In this lecture, we look at velocity. We will look at velocity using average velocity and instantaneous velocity as physical examples of the ARC and the IRC. Problems in velocity provide nice physical examples of the ARC and the IRC in our everyday lives. A standard physical interpretation of the ARC and IRC occurs when we consider motion. Consider the motion of a particle in a straight line. As the position S of the particle changes over time, we ask about the rate of change of position with respect to time. This is velocity. The average velocity of a particle is the ratio of the distance traveled to the elapsed time. So distance is in the numerator, elapsed time is in the denominator. For example, if a car travels 20 miles in 1/2 hour, then the average velocity of the car is 20 miles divided by half an hour, or 40 miles an hour. We view position, or distance, or displacement as a function of time, and so the average velocity is, like any ARC, a slope. It's the ratio of the change in S to the change in T. The average velocity across the interval t1, t2 can be expressed as the average velocity is equal to change in S over change in T, where S here is distance or displacement, and it's a function of the time t. The instantaneous velocity does not involve 2 moments in time, but just one moment. It is the exact velocity of the particle given at an exact moment in time. The instantaneous velocity, or an IRC, can be estimated by the average velocity, but we cannot easily compute the instantaneous velocity since the denominator of our ratio, the elapsed time, has shrunk to 0. The instantaneous velocity is at a single moment in time. Here's an example. A rock falling on the surface of Mars will fall at 1.85 t squared meters in t seconds. Let's find the average velocity of the rock if it falls for 5 seconds from time 0 to time 5, or if it falls from 5 to 5.5 seconds, or across the interval from t equals 5.0 to 5.1. We have here 4 little sub-problems based on an equation for how far a rock travels when it's falling on the surface of Mars. In each of these, we want the average velocity of the rock, and so we're going to have some slope problems. In the first case, in 5 seconds, the rock will fall 46.25 meters. So the average velocity is, it fell 46.25 meters in 5 seconds. The ratio then is 92.5 meters per second. In the second problem, we began with t equals 5. At that point, the rock had fallen 462.5 meters, and after 5.5 seconds, according to my calculator, it had fallen about 560 meters. So the rock had fallen an additional 97 meters in the last half second. How fast is it traveling on average during that half second? Well, if it traveled 97 meters in half a second, its average velocity is this ratio, about 194 meters per second. The other two problems are similar. If we go from 5 to 5.1, we look at the change in y on top, or the change in distance on top, and the denominator is a change in time, or 0.1 seconds. Compute the ratio, we get 186 meters per second. And if the interval is smaller, we end up getting this answer, 185.185 meters per second. All 4 of these problems are a slope problem. Change in distance divided by change in time. But we are more interested in the instantaneous velocity of the rock at 5 seconds. So from the solutions of our previous problem, getting numbers like 194 point something, 186 point something, 185 point something, the velocity seemed to be around 185 meters per second. As we made our intervals smaller and smaller, the numbers got closer and closer to 185. When I was a teenager driving around town in my red Volkswagen Beetle, I was told by friends about a speed trap out near the local park, Glenwood Park. According to my friends, a police car would sit off the road in the bushes near the top of a hill and catch speeders as they came over the hill. Now, this was in the days before radar, and the speed limit on that stretch of road was 35 miles per hour. If they were not using radar back in the 20th century, How did the police decide if I was speeding? Here's how. In those days before radar, the police marked out a portion of the highway, let's say 300 feet, and they marked it with possibly a painted line at both ends. Then when a car crossed one mark, the officer would start his stopwatch. And then he would stop the stopwatch when the car crossed the second line. For example, if the car took 6 seconds to cross the 300 feet, then that 6 seconds gave some information. Knowing that the distance traveled was 300 feet, we had the change in distance is 300 feet, the change in time is 6 seconds, so the ratio is 50 feet per second. So the average velocity of the car across that 100 yards is 50 feet per second. Now, things are measured in miles per hour. This is just under 35 miles per hour. 50 feet per second is about 34 miles per hour. And so if you took 6 seconds to cross that interval, you would not get a ticket. The stopwatch in the police officer's hand is measuring time, which is in the denominator of our slope formula. And so if the time was shorter, then one was obviously going faster. And a car crosses these 300 feet in 6 seconds, it's doing fine. If it does it in 5 seconds, well, it's going a little bit faster. And in fact, you can create a table. Here's a table. It has 3 columns. The first column on the left is the seconds elapsed to cover 300 feet. The middle column is a quick computation of the velocity, average velocity in feet per second. And then the last column translates average velocity into miles per hour. If you look at this table and notice that if you took 5 seconds, not 6 seconds, to cross these 300 feet, then your velocity in feet per second is 60 feet per second in red, and so your velocity is about 41 miles per hour. So if you took 5 seconds, you might be risking a speeding ticket. And if you took even fewer seconds, say down at the bottom, 3.5 seconds, where you're going 58 miles an hour in a 35-mile zone, you would certainly get a ticket. Looking at this table, one can understand if the police officers decide to pull over someone crossing that 300-foot patch in less than 5 seconds. How do you defeat this? This is days before radar, and if you're measuring everything by a stopwatch, then what you do is, when you come over the hill and you realize that there's a police officer off in the bushes, a police car, then you slam on your brakes and you slow way down. And as long as you take at least 6 seconds to cross that patch, you look like you're following the speed limit. The severity of the ticket depends on whether or not you take 4.9 seconds or 4.0. If you took 4.9 seconds, according to the stopwatch, your velocity was on average 41 miles an hour. If you took 4 seconds, your velocity was 51 miles an hour. So you'd get a different ticket depending upon how fast you were. But that's an average. In theory, one could go over the hill at 100 miles an hour, 147 feet per second, slam on your brakes, better do that in the first second, and slow way down so that it takes you 6 seconds to cross this interval, and you would appear to be within the law. All the police officers could measure was an average speed. As a teenage driver, I knew that if I was driving too fast and I suddenly saw a police car off in the bushes, I might quickly slow down and maybe still be okay. In the 50 years since then, how have police departments defeated this slam on the brakes approach to speed limits? By finding ways to measure the change in time in much smaller intervals and so make the average velocity much closer to the instantaneous velocity. Indeed, today, the modern radar gun essentially measures instantaneous velocity. By measuring the Doppler effect of a moving object on a radar pulse, the radar gun picks up instantaneous velocity, not an average velocity. If a car's instantaneous velocity has already been measured with a radar gun, it does no good to slam on the brakes. Indeed, if your velocity has already been measured by a radar gun, slamming on the brakes probably tells the officer that you know you're traveling too fast. In summary, we always want the instantaneous rate of change, or here, the instantaneous velocity, not the ARC. And technology in the middle of the 20th century has allowed police departments to move from average velocity, which was approximations, to instantaneous velocity. And so, of course, everybody's happier. The ARC is the slope of a line between 2 points on the curve. The IRC is the slope of the curve at a particular point. We get the IRC by approximating it with the ARC. These concepts appear in a variety of places with different terminology. And so I'll put here a table. On the left is a variety of ways we write out the average rate of change. The average rate of change is m subsecant. It's the slope of the secant line. It's the ARC across an interval. It's the slope delta y over delta x. There's another formula using the function for delta y over delta x, and so on, or the average velocity. The instantaneous rate of change, on the other hand, is the slope of the tangent line. It's instead of using delta y over delta x, we use dy dx, and as we'll see later, it's going to be f prime of x naught. It's the derivative at a particular point. The ARC is really just a concept we use to get us to the IRC. We really want the IRC, the slope of a function at one point. The slope of a function is also called the derivative, and we'll spend some time in this class learning to compute the derivative of an arbitrary function. We precisely describe the IRC as a limit of the various values of the ARC as the second point approaches the first point P. And so a discussion of limits will be the next concept that we study.